universe expands faster than anyone expected. Galaxies drift away from one another, like embers carried by a wind no one can see. Astronomers once believed that gravity, the great sculptor of the cosmos, would slow this outward motion with time. After all, every galaxy, every star, every atom exerts a pull on every other. The universe should have been coasting to a gradual halt, or perhaps preparing for a long, slow collapse back into itself. But it was not. The expansion was speeding up. This revelation arrived at the end of the 20th century, when teams observing distant stellar explosions known as Type 1, a supernovae, tried to measure how quickly the cosmos was stretching. These supernovae act as cosmic lighthouses, their brightness predictable enough to serve as markers of distance. When the data came in from telescopes in Chile, Hawaii, and space itself, something felt wrong. The explosions were fainter than expected, meaning they were farther away than the models allowed. The only conclusion was unsettling. The universe was not just expanding, it was accelerating. To account for that, cosmologists proposed an invisible energy filling space itself. They called it dark energy, a name that said everything and nothing at once. It would make up nearly 70% of the universe, yet it could not be seen, touched, or detected by any experiment. Its nature remains one of the greatest mysteries in science. The equations of Einstein's general relativity can accommodate such a term. In fact, he had introduced something similar long before, a mathematical constant to keep the universe static. When it was discovered that the universe was expanding, he abandoned it and called it his greatest blunder. Now his so-called blunder had returned from the grave to dominate modern cosmology. But some physicists were uneasy. They looked at the data and wondered whether the acceleration might be a cosmic illusion. What if the universe did not need dark energy at all? What if the problem was not with the cosmos, but with where we are inside it? They imagined a scenario both simple and radical. Perhaps we live in a vast underdense region, a kind of cosmic valley surrounded by richer, denser regions of galaxies. In such a place, the local expansion rate could differ from the global average. If we happen to observe from inside that valley, light from distant regions would reach us distorted by the geometry of space itself. It might look as if the whole universe were accelerating, even though it is not. This idea is known as the void hypothesis. It does not require exotic forces or unseen energy, only an acknowledgement that the universe is not perfectly uniform. The standard cosmological model assumes that on large scales, the cosmos looks the same in every direction and at every location. Yet when astronomers map galaxies across billions of light years, they find a cosmic web of filaments and voids, structures as intricate as neural networks. Between these filaments lie immense regions almost empty of matter. These are the voids, cosmic caverns stretching hundreds of millions of light years across. If we happen to live near the center of one of these underdense bubbles, our observations would betray a subtle bias. Light traveling through a region of lower density would redshift more than expected, its wavelength stretched by the slower gravitational pull. Distant galaxies would appear to recede faster, not because they are truly accelerating, but because the fabric of space between them and us is less dense and therefore expands differently. To an observer inside such a cosmic hole, the universe would seem to speed up. The void scenario gained new life as astronomers encountered more puzzles. Measurements of the Hubble constant, the rate of cosmic expansion today, began to disagree depending on how they were taken. Observations from the early universe using the cosmic microwave background gave one value. Observations of nearby galaxies and supernovae gave another, higher one. The difference was not small. It hinted that something fundamental might be missing from the standard model. Some proposed new physics, new particles, or modified gravity. Others pointed again to cosmic inhomogeneity. Maybe the reason we measure expansion differently in different ways is because we are not in a typical region of the universe at all. Our cosmic neighborhood supports this possibility. The Milky Way does not sit in a dense cluster, but on the edge of an immense emptiness known as the local void. Beyond it lies the Virgo cluster, the nearest large congregation of galaxies, and farther still, the Laniakea supercluster, a sprawling region that binds many thousands of galaxies together through the faint tug of gravity. Within this cosmic geography, our position is not central, not privileged, but it is certainly unusual. For those who study the deep structure of space, this raises a profound question. Could the very acceleration that reshaped modern cosmology be an artifact of our vantage point inside a vast hole in the cosmic web? Could the universe that seems to rush apart faster and faster be nothing more than light crossing uneven terrain? To imagine this is to picture space as a landscape of hills and valleys sculpted by matter itself. In the dense hills of galaxy clusters, gravity slows time and bends light inward. In the empty valleys of cosmic voids, time runs faster and light races freely outward. If we live inside one of those valleys, our clocks would tick slightly differently from clocks in denser regions. The universe we see would seem to evolve at a different pace. What appears as acceleration could instead be the unfolding of this subtle time difference. The mathematics for such a picture exists. It is known as the Lemaitre-Tolman-Bondi solution to Einstein's equations. It describes a universe that is spherically symmetric but not uniform, where density changes smoothly with distance from a center. In these models, there is no need for dark energy. The apparent acceleration arises naturally from the geometry of the void itself. To observers inside, galaxies seem to speed away ever faster, though the underlying space-time follows Einstein's rules perfectly. Yet this explanation, elegant as it is, carries a quiet unease. It places us in a special location, near the center of an immense cosmic depression. That idea clashes with the Copernican principle, the philosophical cornerstone of modern astronomy, which says we are not special. Every observer should see roughly the same universe, but perhaps that principle, though comforting, is not sacred. The cosmos does not owe us symmetry. It only obeys the laws of physics. If this void picture were true, it would change how we interpret nearly every observation in cosmology. Distances, ages, the inferred size of the universe, even the composition of its contents, would need recalibration. The dark energy that now fills textbooks could vanish like mist, replaced by the quiet curvature of our own cosmic surroundings. But proving or disproving this requires exquisite precision, measurements of galaxies and supernovae across vast distances, comparisons of cosmic microwave background maps with local structure surveys. The work continues, and the tension between data sets remains unresolved. For now, dark energy remains the favored explanation, though it is a placeholder for ignorance more than understanding. The universe still refuses to add up cleanly. Its equations balance only when an invisible force is written in to fill the gaps. Scientists live with this discomfort because the model, incomplete as it is, describes the data with astonishing success. Yet in the quiet corners of theoretical physics, the question persists. What if the acceleration is not real? What if we have mistaken the shape of the universe for its fate? To understand this possibility, we must step back and see how cosmic structure forms in the first place. The universe is not a smooth sea, but a frothing web of matter and emptiness. To grasp what it means to live inside a bubble in space-time, we must first explore how those bubbles come to be. And that leads us to the hidden skeleton of the cosmos itself. In the deep night sky, every distant light is a whisper from the past. When astronomers point their telescopes toward the faintest galaxies, they do not see the universe as it is, but as it was billions of years ago. Light needs time to travel, and the farther it journeys, the older its message becomes. That means we live surrounded by layers of history, like shells of ancient glass expanding outward through time. The faintest flicker of radiation that reaches us today began its voyage when the universe was less than 400,000 years old, long before stars or galaxies existed. That glow, called the cosmic microwave background, is the oldest light we can ever see, the afterimage of creation itself. It was from that light that scientists reconstructed the standard model of cosmology. The picture seemed elegant. The universe began in a hot, dense state and has been expanding ever since. Matter gathered into clumps under gravity, forming stars, galaxies, and clusters. On the largest scales, space should look the same everywhere, statistically smooth, its density uniform. But that assumption may hide a deeper truth. When the cosmic microwave background was first mapped in exquisite detail, faint irregularities appeared. They were tiny temperature differences, just a few parts in 100,000, but they hinted at a cosmic web already forming. Regions slightly denser than average would grow into clusters and filaments. Those slightly emptier would evolve into voids. Over billions of years, the contrast between these regions grew more extreme. Matter flowed like water down invisible gravitational slopes, pooling into nodes of high density, while empty regions ballooned outward. Today, those voids dominate the volume of the universe. If you could shrink yourself to the scale of a galaxy and drift through space, you would find the cosmos resembles a vast three-dimensional sponge. Filaments of galaxies thread through the emptiness like glowing strands, while enormous cavities stretch between them, each hundreds of millions of light-years wide. Inside these voids, the density of matter can be less than a tenth of the cosmic average. They are not truly empty, but their darkness is almost absolute. The existence of such immense hollows changed how astronomers think about the universe. The Sloan Digital Sky Survey, one of the most ambitious mapping projects in history, charted the positions of millions of galaxies across a cosmic volume so large that its patterns revealed the skeleton of reality itself. Later missions, such as the Dark Energy Spectroscopic Instrument and the European Space Agency's Euclid Observatory, refined the picture further, mapping not only where galaxies are, but how they move. The result is a living portrait of structure formation. The universe growing like a living organism with filaments for veins and voids for lungs. In that grand architecture, our Milky Way finds itself not in a bustling city of galaxies, but on the quiet outskirts of an enormous underdense region known as the local void. To understand what this means, imagine a boat adrift in a slow-moving current. To an observer inside the boat, nearby markers might appear to drift apart if the current varies with position. In a similar way, the expansion of space can appear faster inside a region of low density, where gravity exerts less pull to resist the cosmic flow. If we inhabit such a region, then our measurements of cosmic acceleration might be distorted by that gentle gradient. Light from distant galaxies must cross boundaries between denser and emptier regions, and as it does, its energy changes subtly. To us, the effect would mimic an acceleration of the universe's expansion. Some cosmologists, like David Wiltshire and Subir Sarkar, have explored this idea through models that relax the assumption of uniformity. They argue that what we interpret as dark energy could arise naturally from the way different regions of the universe evolve at different rates. Inside a void, time flows slightly faster than in a dense cluster. If most of our observations come from within such a void, our cosmic clock would tick differently from the average clock of the universe. When we compare our measurements to the early universe, we would see an apparent acceleration that is not real, but emerges from the uneven passage of time. The mathematics behind this concept is subtle but beautiful. In Einstein's general relativity, space and time are shaped by energy and matter. Where there is less matter, space expands more freely. Where there is more, it curves inward. The balance between these effects determines the overall geometry of the universe. In the void models, this geometry varies smoothly with position, so that local observers everywhere still see a nearly isotropic sky, yet the global picture diverges from uniform expansion. No special forces are required. The illusion of dark energy arises from perspective alone. Critics argue that such models are fine-tuned. To match observations, the void must be vast, on the order of several billion light-years across, and we would need to be located close to its center to avoid obvious anisotropies in the cosmic microwave background. That feels unlikely, though not impossible. After all, Improbable things happen somewhere in an infinite cosmos. Others point out that surveys of galaxy distributions show the local universe to be underdense by roughly 20 to 30% compared with the cosmic average, but not empty enough to explain the full acceleration. Still, the discrepancy between early and late measurements of the Hubble constant keeps the debate alive. The tension between models reflects a deeper philosophical divide. On one side lies the cosmological principle, the belief that we occupy no special location and that the universe looks the same in all directions. On the other lies the possibility that our cosmic address matters, that local structure influences our perception of reality. If the latter is true, then cosmology is not a single story told from nowhere, but a set of overlapping stories told from different places in the web. Whether or not we live inside a vast cosmic whole, the idea forces us to reconsider what we mean by observation itself. Every beam of light we measure has traveled through a changing landscape of space-time. The farther it comes, the more that landscape affects its message. Perhaps the universe's apparent acceleration is not a new force, but a mirage produced by our location in that landscape. To test that, scientists are pushing for more precise maps of both nearby and distant galaxies, seeking patterns that might betray the curvature of our region. If our local expansion differs from the average, the fingerprints of that difference will appear in how galaxy flows deviate from pure uniformity. Even if the void hypothesis fails, it serves as a reminder that perception and reality are not the same. The universe that we reconstruct from light is filtered through geometry, gravity, and time. What we call the cosmos might be less an external object than a projection of our position within space-time itself. Every measurement we make is an echo bouncing off the curved walls of the whole we inhabit. And perhaps that is the point, to learn that the cosmos, vast and indifferent, still depends on where we stand to look at it. In the quiet mathematics of the universe, beauty and unease often share the same line. The idea that we might live inside a cosmic void is both elegant and disturbing. Elegant, because it would mean the universe needs no mysterious energy to explain its motion. Disturbing, because it would mean that what we perceive as the entire cosmos is shaped by the emptiness surrounding us. To most people, emptiness sounds like nothing, but in cosmology, nothing is never truly empty. Even a void hums faintly with radiation, ghostly particles, and quantum fields that fluctuate just enough to keep space-time alive. In the underdense expanses between galaxy clusters, space itself stretches more freely. The gravitational grip that binds galaxies together weakens, and the remaining matter drifts outward, thinning further. The deeper the void, the faster this expansion becomes. The physics follows Einstein's equations exactly, but the perception of it depends on where the observer sits. Inside a void, clocks run ever so slightly faster than in the dense walls of the cosmic web. This difference is infinitesimal over a single lifetime, but immense over cosmic time. Over billions of years, even a small difference in the rate of time could make the expansion of space appear to accelerate. Our instruments do not measure the universe directly. They measure the light that has crossed these differing regions, carrying with it the fingerprints of time's uneven flow. When the discovery of cosmic acceleration was first announced, many scientists wondered whether the data might hide such effects. Yet the void idea was largely set aside because it required breaking the Copernican principle, that ancient rule inherited from the revolution of Copernicus himself. We are not at the center of anything. But perhaps the principle was never meant as a law of nature, only as a caution against arrogance. The universe does not promise us anonymity. It only promises that whatever laws we find here, they hold everywhere else. If our cosmic environment is indeed special, it may be because of how structure forms from quantum randomness. The early universe was seeded by minute fluctuations in density, amplified over eons by gravity. Some regions became rich in matter, others drained into hollows. If enough cosmic time has passed, our region could have expanded into a bubble of relative emptiness, not through accident, but through the natural evolution of space. Living inside such a region would not violate physics, only our expectations. As the debate continues, new missions seek to refine the map of cosmic expansion. Observatories like Euclid and the Vera Rubin Observatory will chart the positions and motions of billions of galaxies. Their measurements of baryon acoustic oscillations, subtle ripples left over from sound waves in the early universe, will help test whether expansion truly accelerates uniformly or varies with environment. If the data reveal even a slight asymmetry in how galaxies recede from us compared with other directions, it could hint that our cosmic neighborhood is less typical than we imagine. But for now, the deeper mystery remains unresolved. Dark energy still floats at the heart of the Standard Model, a mathematical necessity wrapped in ignorance. Its name is poetic because it describes not what it is, but what we do not know. Yet the possibility that its effects arise from geometry rather than substance offers a strange comfort. It means the universe may not be ruled by something unseen and inexplicable, but by the familiar curvature of space-time itself, sculpted by the same gravity that holds the stars in place. Imagine, then, that the universe is not accelerating. Imagine that what we see is the slow breathing of a cosmic cavity, a region of lower density expanding gently within the larger web. To us, it feels like the cosmos is racing away, but to an observer far beyond our void, it might look ordinary, calm, almost still. The illusion of acceleration would be the signature of our isolation. We would be inhabitants of a bubble so large that it defines our entire perception of reality. Such a picture forces us to confront the fragility of our cosmic understanding. Every observation depends on our frame of reference, every truth shaped by the curvature of the space we occupy. The more we learn, the more the universe reveals itself as a hall of mirrors where perspective and physics are inseparable. Perhaps one day, we will measure enough light from distant galaxies to know for certain whether dark energy is real or whether our void simply deceives us. Until then, we live inside a question, surrounded by the faint afterglow of creation and the long silence of space. The universe does not add up, not yet. And maybe that is its most haunting beauty. It allows us to wonder whether the acceleration we see is not the universe running away from us, but the echo of the emptiness we inhabit. The universe, when seen on the larger scales, looks nothing like the smooth ocean of stars we once imagined. It is a grand architecture of matter and void, a three-dimensional lacework that stretches across billions of light years. The galaxies do not scatter evenly through space. They align along invisible threads, gathering into filaments that twist and converge into clusters. Between those filaments lie the voids, immense caverns of near-nothingness so vast that compared to them, entire galaxy clusters are mere specks adrift in a sea of darkness. This discovery reshaped cosmology. In the 1970s, when astronomers began mapping the redshifts of galaxies, how much their light was stretched by the expansion of space, they noticed something odd. Instead of forming a random cloud, galaxies arranged themselves into sheets and walls with enormous empty regions between them. Later, the Sloan Digital Sky Survey would reveal this pattern in breathtaking detail. With millions of galaxies plotted, a cosmic web appeared, its filaments glowing like tendrils in a dark fluid. For the first time, humanity could see the skeleton of the universe. These structures arise from the dance between gravity and time. In the early universe, matter was nearly uniform, with only the tiniest variations in density, differences of 1 part in 100,000. Those fluctuations were frozen into the cosmic microwave background, the first light that escaped when the universe became transparent. Over billions of years, gravity magnified those imperfections. Slightly denser regions pulled in more matter, becoming denser still, while emptier regions lost matter and expanded faster. Like a soap bubble forming between drops of liquid, the voids grew and connected, pushing matter into thin filaments and nodes. If you could fly through this structure at light speed, you would see a landscape more intricate than any neural network. galaxy clusters would appear as glowing knots where many filaments intersect, while enormous spaces of darkness stretch between them for hundreds of millions of light years. Inside those spaces, only a few lonely galaxies drift in slow silence, their starlight diluted by the emptiness around them. The universe may look full of stars from our small vantage point, but in truth, it is mostly hollow. Our own Milky Way lies in one of the quiet suburbs of this cosmic metropolis. We sit near the edge of the local void, a region of lower density, roughly 200 million light-years across. On one side lies the Virgo cluster, the nearest great congregation of galaxies, and farther beyond that, the Laniakea supercluster, a gravitational domain spanning more than 500 million light-years. Within this vast web, the local void is a cavity, dark, silent, expanding faster than the regions around it. Galaxies near its edges are slowly being pulled outward, flowing toward denser filaments. Astronomers discovered the local void not by seeing it directly, but by noticing how galaxies move. Those near our position show peculiar velocities, small deviations from the general expansion of space, as if being pushed away from an empty region behind us. The galaxies in the direction opposite the Virgo cluster appear to recede slightly faster than expected, while those toward Virgo are slower, pulled toward its gravitational mass. The best explanation is that we live near the boundary of a great emptiness, and the gravity of the surrounding filaments is tugging us toward them, while the void expands behind us. In the grand cosmic hierarchy, voids are far more common than clusters. They occupy most of the universe's volume, though they contain only a small fraction of its mass. Astronomers categorize them by size: mini-voids tens of millions of light-years across, and supervoids stretching nearly 1 billion light-years wide. These are not random gaps, but part of the universe's self-organizing geometry, the outcome of gravitational instability acting on an initially smooth medium. Matter collapses into filaments, and space between them relaxes, creating expanding bubbles of low density. Some voids, like the Eridanus supervoid, have even been linked to anomalies in the cosmic microwave background. In that direction of the sky, the background radiation appears slightly colder than average. One explanation is the integrated Sachs-Wolf effect. Light passing through an underdense region loses a bit of energy, arriving cooler than light that travels through denser space. Such interactions reveal that voids are not just empty holes. They are dynamic features that affect light, time, and the apparent geometry of the cosmos. The Euclid mission, launched by the European Space Agency, and the Dark Energy Spectroscopic Instrument on Earth, are designed to map this web with unprecedented precision. By measuring redshifts of tens of millions of galaxies, they will construct a three-dimensional atlas of the universe. These maps will let scientists study how matter clusters and how voids evolve, providing new tests for cosmological models. If dark energy is real, its influence should appear in the way large-scale structures grow over time. But if the apparent acceleration of the universe arises instead from our location inside a vast void, then these surveys might expose the subtle asymmetry hidden in the data. To picture this web is to confront the immensity of cosmic architecture. The filaments are like veins through which galaxies flow, and the voids are the lungs that breathe expansion into the universe. Everything moves, drawn by gravity, stretched by the growth of space. Yet the pattern remains, a frozen echo of the early universe's quantum tremors. It is humbling to realize that most of existence is emptiness, and that the bright galaxies we see form only a thin scaffold around the dark. If we truly live within a cosmic whole, that whole is not a boundary, but a structure within a structure, a bubble in an endless foam of bubbles. Each one expands at its own pace, each shaped by the local balance between matter and emptiness. From inside, the view feels uniform, but from the outside, it would reveal gradients in density, motion, and time. The cosmic web is not just a map of where galaxies are, it is a map of how the universe thinks, an imprint of the laws that govern expansion and gravity woven into space-time itself. From a distance, the cosmic web looks serene. But within it, matter and gravity are in constant negotiation. Galaxies drift along invisible highways of dark matter, flowing like sediment down a cosmic riverbed. The filaments that connect them are not mere strings of stars. They are colossal structures composed of both ordinary matter and the unseen dark matter that outweighs it 5-1. The galaxies are like lanterns, tracing the shape of something larger and hidden. When scientists speak of dark matter, they do not mean darkness in a poetic sense. They mean literal invisibility. It neither emits nor absorbs light, yet its gravitational presence sculpts the universe. Without it, galaxies could not have formed. In computer simulations of cosmic evolution, when physicists let only normal matter interact, the result is chaos. Gas collapses too quickly, stars ignite too soon, and structures disintegrate. But when dark matter is added, it provides the scaffolding that holds galaxies together. Gravity pulls it into filaments that span the cosmos, and ordinary matter follows, settling into the valleys it carves. Inside those filaments, galaxies swarm together, forming superclusters and walls that define the borders of the voids. The largest known of these walls is the Hercules Corona Borealis Great Wall, a structure spanning 10 billion light-years. It is so immense that light needs more time to cross it than the universe has existed since the birth of the first galaxies. Its discovery challenged the assumption that the cosmos should be homogeneous on the largest scales. How can such a colossal pattern exist in a universe that is supposed to be uniform? Some suggest it is an illusion born from incomplete data. Others see it as evidence that our understanding of cosmic structure is still in its infancy. Even nearer to home, the patterns are astonishing. The Perseus-Pisces supercluster stretches across 300 million light-years, forming a curved chain of galaxies like pearls on an invisible thread. The Coma cluster, dense with thousands of galaxies, anchors one intersection of this web. Between these islands of light, the voids yawn vast and silent. They are the negative spaces of the universe, their boundaries defined not by matter, but by its absence. Yet these voids are not passive. They expand as the universe grows, pushing their boundaries outward, forcing the filaments closer together. The universe is like a foam of soap bubbles, where the edges shrink as the spaces within swell. The local void, where we reside, participates in this silent expansion. Observations of nearby galaxies show that they are receding slightly faster than the Hubble law predicts, a hint that the space around us is less dense and therefore stretches more readily. This behavior aligns with predictions from models of void dynamics. Gravity in denser regions slows expansion, while in emptier regions, space expands faster. Over time, this difference amplifies, deepening the contrast between full and empty. In that sense, the universe is both growing and hollowing out at once. To map these differences, astronomers rely on surveys that measure redshift and distance with extraordinary accuracy. Redshift tells how much the wavelength of a galaxy's light has been stretched by cosmic expansion. Distance tells how far that light has traveled. By comparing the two, scientists can chart the rate of expansion in different directions. If our region were truly an enormous underdensity, the pattern of redshifts would reveal a subtle anisotropy, a difference in how expansion appears along different lines of sight. So far, the data suggest near uniformity, but tiny deviations remain, teasing the possibility that our cosmic neighborhood is special after all. There is also a philosophical weight to these discoveries. The cosmic web erases any lingering dream of a simple, smooth universe. Instead, it shows us a cosmos shaped by chance, complexity, and emergence. The patterns of filaments and voids arise not from design, but from the chaotic growth of gravity acting on primordial noise. Every galaxy, every star, every atom is a consequence of that interplay. And yet, the result is not random chaos. It is structured beauty, self-organizing order on a scale beyond imagination. The voids themselves act as laboratories for cosmology. Because they are less affected by nonlinear gravitational collapse, their expansion is easier to model. Their emptiness allows precise tests of the laws of gravity and the nature of dark energy, or its alternatives. Some researchers even search for differences in how light travels through voids compared to denser regions, hoping to catch the signature of modified gravity or exotic physics. The fact that we may inhabit one of these voids makes our vantage point a natural observatory for such effects. Inside this web of matter and emptiness, everything that exists moves not through stillness, but through the slow breathing of space. Even light, which seems to travel in straight lines, bends gently under the weight of invisible structures. The paths of photons from distant galaxies curve as they cross filaments and voids, distorting the shapes of background objects. This phenomenon, called gravitational lensing, allows astronomers to see the otherwise invisible distribution of mass. It turns the universe itself into a cosmic lens, focusing and stretching light across billions of light years. When you gaze at the night sky, the constellations appear static, but in truth, they are part of a moving ocean. The galaxies beyond them are not fixed points, but swimmers in an expanding current, their positions shifting by kilometers per second. Over cosmic time, the constellations will dissolve, the Milky Way will merge with Andromeda, and the entire local group will drift toward the Virgo cluster. The grand ballet of structure never ceases. It merely moves at a pace too slow for human eyes to see. And within that slow motion lies a question. If the cosmic web defines the shape of everything we can see, what defines the shape of everything we cannot? Could the voids themselves conceal deeper geometry, curvatures of space-time that trick our perception of the whole universe? Perhaps the hole we inhabit is not merely a gap between galaxies, but a feature woven into space-time's fabric. To uncover that possibility, we must look beyond the web's visible threads and into the models that describe how light and matter behave when space is no longer uniform. The deeper astronomers peer into the universe, the clearer it becomes that the cosmic web is not merely a map of galaxies, but a record of space-time itself, stretching and folding over billions of years. Every filament, every void, every cluster is a fossil of expansion, a shape carved by gravity from the initial whisper of quantum fluctuations. The web is the universe remembering how it grew. In this intricate lattice, matter is only the visible tip of something far more profound. Most of what shapes the universe lies in the unseen. Dark matter forming its bones, and perhaps dark energy, or the illusion of it, filling its lungs. The filaments connect galaxy clusters into immense bridges that reach across light years counted in the billions. At their intersections, superclusters form, while in between, vast empty regions continue to swell. Space expands most freely where it is least encumbered by matter, so the voids grow faster than the rest of the universe. This differential expansion stretches the filaments thinner and elongates them, as if the cosmos itself were breathing out. Inside the local void, our Milky Way glides on the edge of an invisible frontier. To one side, gravity from denser regions tugs us inward. To the other, the emptiness behind us allows us to drift outward. Astronomers tracing the motions of nearby galaxies see this cosmic tide at work. Some galaxies fall toward the Virgo cluster, while others slide away into the deep of the local void. It is a delicate balance, like floating at the edge of a cosmic cliff, feeling both the pull of mass and the push of emptiness. This balance hints at a fundamental truth. The universe's structure is not random, but neither is it centrally planned. The same equations of general relativity govern every corner of space, yet their solutions manifest differently depending on local density. Where matter gathers, time slows, and light bends inward. Where matter thins, time speeds up, and space stretches outward. The cosmic web is the natural consequence of these competing rhythms. It is space-time's attempt to equalize itself, to balance curvature and emptiness across an unfathomable scale. When cosmologists simulate the evolution of the universe on supercomputers, they feed in the laws of physics and a nearly uniform early density field. The result that emerges after billions of simulated years is astonishingly familiar. A web of filaments and voids, nearly identical to what telescopes observe. That agreement is one of the triumphs of modern cosmology, a sign that Einstein's equations, written over a century ago, still trace the contours of the universe with uncanny precision. Yet within that triumph lies a riddle. If the equations reproduce the web so perfectly, why do they still require the mysterious addition of dark energy to explain its growth? Could it be that the geometry of the web itself, with its vast underdensities, already contains the illusion of acceleration? The distinction between geometry and energy blurs in general relativity. Space tells matter how to move, and matter tells space how to curve. In a universe filled with uneven density, the curvature of space varies from place to place, altering how light travels and how time flows. To an observer inside one of those underdense regions, distant galaxies appear to accelerate away, though the underlying space-time may not be accelerating at all. The cosmic web might therefore be more than a structure. It could be a lens through which we misread the universe's expansion. If so, the voids are not passive backgrounds, but active participants in cosmic evolution. They shape the apparent rate of expansion and even influence how we estimate the universe's age. A photon that journeys through a void spends more time in fast-expanding space, stretching its wavelength more than light that passes through denser regions. By the time it reaches us, its redshift encodes both the universal expansion and the extra stretching from the voids it crossed. Our interpretations of distance and velocity rest on that redshift, so a small geometric bias could ripple into a grand cosmological illusion. Even our most precise instruments, like the Hubble Space Telescope and the upcoming Nancy Grace Roman Space Telescope, measure light that has traversed countless voids and filaments. Every beam carries the fingerprints of those encounters, like a letter that has been opened and resealed by 1,000 invisible hands. Correcting for such effects is nearly impossible. The cosmic web is not a uniform medium, but a turbulent ocean of space-time. And we, tiny observers in one corner of it, must infer the rules of the whole by reading the waves around our ship. To many physicists, this uncertainty is not failure, but beauty. The universe resists simplification. Its structures mirror the complexity of the equations that describe them. The cosmic web is a bridge between the tangible and the abstract, a physical manifestation of space-time's mathematics. It shows us that emptiness and structure are two faces of the same reality. The voids give the filaments their shape. The filaments define the void's boundaries. Without emptiness, there would be no form at all. As we continue to map and measure, we edge closer to understanding whether our cosmic neighborhood, the local void and its surrounding filaments, plays a deeper role than we ever imagined. Perhaps we are not merely living near a void, but inside one so vast it colors every measurement we make, bending our perception of the cosmos into an image of acceleration. If that is true, then the whole around us is not a gap in space, but a curvature of reality itself. To test this idea, cosmologists turn once more to theory, to models that describe how an observer within an underdense region perceives expansion. These models, refinements of the Lemaitre-Tolman-Bondi equations, show that light and time behave differently inside a varying density gradient. They open a doorway to a startling possibility, that our entire observable universe might be the interior of a cosmic bubble, a structure that mimics acceleration without invoking any new energy at all. And so the question deepens. If the cosmic web is the skeleton of the universe, what lies in the marrow of that structure? What does it mean to exist inside one of its vast hollows? The next step in this journey leads us to that idea, to the radical vision that perhaps the universe we see is not expanding into emptiness, but expanding within a bubble that defines our very perception of space and time. Imagine for a moment that the acceleration of the universe is an illusion born from geometry. Imagine that the cosmos we observe, its galaxies fleeing ever faster into the dark, is not driven by a mysterious force, but by our position inside an immense bubble of underdensity. This is the essence of the great cosmic bubble hypothesis. It does not defy Einstein's general relativity. It flows directly from it. It suggests that the universe can be inhomogeneous on grand scales, with regions of differing density expanding at differing rates, and that we might inhabit one of those regions without ever realizing it. The mathematics that allows this possibility was discovered long before the concept of dark energy existed. In the 1930s, Georges Lemaitre, a Belgian physicist and priest, and Richard Tolman, an American cosmologist, each explored exact solutions to Einstein's equations that described a spherically symmetric universe with varying density. Later, Hermann Bondi refined these models. Together, they are known as the Lemaitre-Tolman-Bondi solutions, or LTB for short. These solutions describe universes that are not perfectly uniform, universes with a center, a gradient, and the potential for observers who see expansion differently, depending on where they stand. In such a universe, the geometry of space-time itself creates the illusion of acceleration. Suppose we live near the center of a vast underdense region billions of light years across. In that region, space expands faster than in the denser areas outside it. When we observe distant galaxies, their light must climb out of this expanding bubble, passing through regions where space stretches at different rates. The result is an extra redshift, a lengthening of light's wavelength that makes those galaxies appear farther and receding faster than they truly are. To us, that looks like acceleration, yet the equations reveal that no new energy is needed. The effect arises naturally from curvature and density gradients. To grasp this, consider a simpler image. Imagine a balloon covered with dots representing galaxies. If the balloon expands uniformly, every dot sees the others moving away evenly. But if the balloon has a soft patch where the rubber is thinner, that region will stretch faster than the rest. A dot near the center of the thin patch will see its neighbors recede faster than predicted by a uniform model. It will conclude that the entire balloon's expansion is accelerating, though the difference is merely local geometry. The universe, on a far grander scale, could behave in the same way. In this picture, our cosmic bubble could span tens of billions of light years. It would not be empty, but its average density of matter, galaxies, gas, dark matter, would be lower than the cosmic mean. Beyond its boundaries, the universe would continue with higher density and slower expansion. Light from those regions would carry signatures of that contrast. If we could, measure the precise relationship between redshift and distance for galaxies far beyond our local bubble, we might detect a subtle deviation from the predictions of the standard cosmological model. That deviation could reveal whether we live inside a cosmic hole. This idea gained renewed attention in the early 21st century, when cosmologists confronted the so-called Hubble tension. Measurements of the universe's expansion rate from the early cosmos, derived from the cosmic microwave background, disagreed with direct observations of nearby supernova. The discrepancy suggested that either new physics was at play or our assumptions about uniformity were wrong. The void hypothesis offered a natural bridge. If our local region expands faster because it is less dense, then local measurements of the Hubble constant would appear higher, while the global average inferred from the early universe would appear lower. The numbers would reconcile without invoking exotic energy or modified gravity. Yet this simplicity conceals a deep unease. The LTB models place us near the center of the bubble, because only from near the center would the universe appear roughly isotropic, the same in every direction, as observations demand. That seems to violate the Copernican principle, which insists that we are not in a privileged location. Many physicists find this distasteful. as though the entire idea smuggles humanity back into the center of the cosmos after centuries of exile. But physics is not a democracy. It answers only to evidence. If the data were to show that our position happens to lie within a vast underdensity, then so be it. The universe does not care where we prefer to stand. To test the bubble idea, scientists use cosmic chronometers, galaxies whose ages can be estimated from the rates at which their stars evolve. By comparing those ages across different redshifts, they reconstruct how expansion has changed over time. So far, the data fit the standard dark energy model slightly better than the pure void model, but the margin is not decisive. Other tests involve the cosmic microwave background. If we lived in a giant void, the background radiation would appear slightly cooler in one direction and warmer in another, due to gravitational redshift across the bubble's edge. Observations show a nearly perfect isotropy, but small anomalies remain. Hints of a dipole asymmetry and unexplained cold regions, like the one in the constellation Eridanus. Whether these clues point to a void or to something else is still unknown. What matters is that the LTB framework shows that acceleration need not be fundamental. It can emerge from geometry alone. The expansion of the universe might be an illusion of perspective, a trick of curved space-time on a cosmic scale. If so, then what we call dark energy could be as imaginary as the crystal spheres once thought to carry the planets. But the bubble hypothesis carries an even stranger implication. If space-time can behave like this, forming vast regions that expand at different rates, then perhaps the boundary of our bubble marks not just a change in density, but a deeper transition in the nature of space itself. The equations of general relativity do not forbid such boundaries. They only describe how curvature behaves when energy and matter vary. Beyond our bubble, the laws might continue smoothly, or they might fold into something we cannot yet imagine. The thought lingers. If our universe's acceleration is a mirage caused by being inside a bubble, what lies beyond its walls? Are we merely in one cell of an infinite cosmic foam, each bubble an island universe of its own? Or does our bubble mark the interior of something larger and far more enigmatic, a hole in space-time whose horizon defines everything we see? Inside the equations of general relativity, space and time are woven so tightly together that emptiness itself can curve. The Lemaitre-Tolman-Bondi models reveal that curvature is not a single, universal property of the cosmos, but something that varies with density. Where matter thins out, space-time bends outward, stretching more freely. Where matter accumulates, it folds inward, slowing expansion. The difference between these two behaviors creates a subtle gradient, a slope not of distance, but of time itself. Inside a massive cosmic bubble, that slope could be so gentle that no observer within it ever suspects it exists, yet so vast that it alters the apparent age and speed of the entire universe. Picture the universe as a sequence of nested spheres, each representing regions of different density. At the center lies the emptiest zone, the bubble's heart, where expansion is fastest. As we move outward, the density rises, slowing the rate of cosmic growth. From inside, the gradient of time between these layers makes light from the outer regions appear older, redder, and farther away than it truly is. Observers inside the bubble interpret this as evidence that the universe's expansion accelerates. To them, distant galaxies seem to recede faster with each new measurement, though the underlying geometry is perfectly consistent with Einstein's field equations. The most astonishing aspect of this idea is how invisible it would be. Because general relativity allows each observer to experience local physics identically, no one inside the bubble could detect a simple experiment proving they are in a special region. Local gravity, atomic transitions, and the motion of nearby galaxies all follow the same rules as anywhere else. Only by comparing distant observations, light that has traveled across billions of light years, can the shape of the larger geometry be inferred. In this way, The bubble is not a cage, but a lens, distorting the entire cosmic panorama without leaving fingerprints on the laws of nature themselves. For decades, cosmologists have sought to find whether this bubble is real. The tension in the Hubble constant remains one of the strongest motivations. Early universe measurements, drawn from the cosmic microwave background, yield an expansion rate lower than that derived from late-time supernovae. If the void model is correct, this discrepancy is no surprise. A region of lower density expands faster locally, so any measurement based on nearby galaxies would overestimate the global rate. The numbers we find would differ precisely as they do. In this sense, the bubble hypothesis not only explains cosmic acceleration, but also reconciles one of modern physics' most puzzling conflicts. Still, skepticism persists. The observed isotropy of the cosmic microwave background places strict limits on how off-center we could be inside such a void. If we were displaced even slightly, the background would show a strong dipole pattern, a directional signature of the gradient in density. Yet the real sky shows only a tiny dipole, mostly explained by our galaxy's motion through space. To satisfy this constraint, we would need to be within a few percent of the bubble's center, a position some consider too coincidental to take seriously. But coincidence, like symmetry, is a human concern. The universe does not design for elegance. Recent observations add complexity to the debate. Large-scale galaxy surveys reveal structures extending hundreds of millions of light-years, vast filaments and voids that already violate the simplest notions of homogeneity. The discovery of the KBC void, an underdense region roughly 2 billion light-years across encompassing our local group, offers empirical support for the idea that such vast cavities exist. If the KBC void influences cosmic expansion even slightly, it could account for part of the observed acceleration. In that case, our universe would not require dark energy at all, only a careful accounting of where we stand inside its uneven terrain. The notion of a universe shaped by geometry rather than mystery carries a quiet elegance. It reduces the unknown not to magic but to mathematics. Yet it also raises philosophical questions. If the apparent acceleration of the universe arises from our location in an underdense bubble, then the cosmos is not a single story told everywhere the same way. It is a mosaic of perspectives, each observer surrounded by their own curvature of space and their own flow of time. What we call the universe may be only our local chapter in a book written across countless regions, each page bent by its own geometry. The bubble hypothesis reframes even the idea of cosmic time. Inside the void, clocks tick faster than in denser regions. That means our estimate of the universe's age could be biased. What we measure as 13.8 billion years might be a local value, the time experienced by our region of spacetime rather than the universe as a whole. Beyond the bubble, where density is higher and time flows more slowly, the cosmos might be younger or older, depending on which frame one chooses to define as standard. There is no universal now, only layers of time flowing at different speeds, stitched together by the curvature of spacetime. This relativity of time turns the bubble from a structure of space into a living geometry, a region where time itself stretches more freely than elsewhere. To live inside it is to experience a slightly accelerated version of cosmic history, to see galaxies aging faster than their counterparts beyond the void's edge. Perhaps that is why we find ourselves in such a region, because time inside a void runs faster, evolution proceeds more quickly, and life arises sooner. It is an anthropic whisper in an otherwise indifferent cosmos. Yet even as the equations support this vision, they open a deeper question. If spacetime can behave this way naturally, forming expanding bubbles of faster time and lower density, then what limits their size? Could the entire observable universe be one such bubble, its apparent acceleration a reflection of curvature on a truly cosmic scale? If so, then our bubble may not be merely part of the cosmic web. It may be the universe itself, the great cosmic whole inside which all existence unfolds. If our universe is a bubble, then it is one of unimaginable scale, expanding not into space, but into time itself. The equations that describe it do not need an external environment. Space-time carries its own momentum. Once curvature begins to stretch, it keeps stretching unless gravity or matter slows it down. Inside such a bubble, every observer believes the expansion to be universal, while in truth, it is local geometry playing out across the whole. In the Lemaitre-Tolman-Bondi framework, the boundary between regions of different density is not a sharp wall, but a gradient. Moving outward through that gradient, an observer would experience subtle changes in the flow of time and the apparent brightness of distant galaxies. Yet because these effects scale gradually, no traveler could ever reach the bubble's edge. They would see the universe fade smoothly from one state to another, a transition as seamless as twilight. To anyone inside, there would be no boundary at all, only the illusion of infinite depth. The most fascinating aspect of this model lies in how it treats light. Photons crossing regions of differing curvature lose and gain energy, shifting their color in ways that mimic acceleration. The path of every beam becomes a chronicle of cosmic history, integrating the effects of local density all along its journey. When those photons arrive in our telescopes, their wavelengths tell a story we interpret as cosmic expansion. But if our entire view is confined within a bubble, then that story is incomplete. We see only the stretching of light within our own domain, mistaking it for the behavior of the universe at large. This possibility redefines what it means to observe. Every measurement in cosmology assumes that we can treat our local neighborhood as typical. If that assumption fails, then all derived quantities, distance, age, even the estimated size of the universe, must be rethought. The cosmic horizon, the farthest light we can see, might not mark a limit of the universe itself, but the boundary of our bubble's influence. Beyond it, the geometry could differ entirely, curving into another region of space-time with its own rhythm of expansion and its own perception of time. Some theorists suggest that such bubbles may form naturally during cosmic inflation, the rapid expansion that followed the Big Bang. Inflation is thought to have ended at slightly different times in different regions, leaving behind pockets that expanded faster or slower, depending on how the quantum fields decayed. Our observable universe could be one of those pockets, a relic of an inflationary process that created countless others. Each bubble would contain its own version of cosmic history, its own laws of physics subtly tuned by its initial conditions. In that sense, the Great Cosmic Bubble hypothesis blends into the concept of the multiverse, though it arises from geometry alone rather than from speculative new dimensions. If this vision is correct, then our universe is not the whole, but a region of relative emptiness within a far grander structure. The cosmic microwave background, rather than being the final word on the early universe, could be the imprint of our bubble's boundary, the last surface from which light could reach us before curvature turned inward. The faint ripples and asymmetries in that ancient glow might be the fingerprints of neighboring regions, faint reflections of other bubbles pressing against ours in the fabric of space-time. To live inside such a bubble would not change our daily lives, yet it would redefine what we mean by reality. Our physical constants, our perception of time, even our idea of cosmic destiny would all be local phenomena, shaped by the curvature of the void we inhabit. The acceleration we see would no longer be evidence of a mysterious energy driving the cosmos apart, but a gentle reminder of our perspective within a grander geometry. The universe might not be expanding into nothing. It might be relaxing within its own curvature, like air diffusing inside a soap bubble that has no outside. But the mind resists this idea because it asks us to give up the comfort of an external truth. If our observations are shaped by the void around us, then the cosmos we describe is not a mirror of objective reality, but a projection of our position within it. Even our most precise instruments become storytellers, bound by perspective. In that realization lies both humility and awe. The universe does not lie to us. It only speaks in the language of geometry, and we have only begun to learn its grammar. From here, a still deeper question unfolds. If a bubble of space-time can mimic the behavior of an entire universe, could such a bubble exist within something even larger? Could the whole we inhabit be not just a region of underdensity, but the interior of a deeper gravitational structure? A black hole, perhaps, whose horizon defines the limits of everything we see. Some equations suggest this is not only possible, but inevitable. To follow that thread is to step beyond the idea of voids and into the heart of gravity itself. If the universe is a bubble, perhaps it floats inside a greater abyss, its boundary marked by the same kind of horizon that surrounds a black hole. The next question is no longer whether we live in a void, but whether we live inside an event horizon. The idea sounds impossible at first, like something whispered from the edge of reason. Yet within the mathematics of general relativity, the boundary between a universe and a black hole is not as clear as it seems. A black hole is defined by its event horizon, a surface beyond which light cannot return. Inside that horizon, space and time exchange roles. What we call the future outside the hole becomes a direction inward. Space falls, time flows differently, and the singularity that lies at the center is not a point in space at all, but a moment in time, a destination every path must eventually reach. Now imagine that instead of collapsing into a singularity, space-time inside a black hole continued expanding. The interior would behave like a new universe, isolated from the one outside by the event horizon. To an observer within, that expansion would look exactly like the cosmos we see. Galaxies rushing apart, time flowing forward, horizons beyond which nothing can be seen. The equations do not forbid this. In fact, they quietly allow it. The first to suggest this was the physicist Pathria in 1972, who noticed that the equations describing the interior of a black hole resemble those describing an expanding universe. Later, researchers such as Eason and Brandenburger refined the idea, proposing that our Big Bang might not have been a beginning at all, but the explosive rebirth of matter from a collapsing star in another, older cosmos. In this view, every black hole could give birth to a new universe on the inside, separated from its parent by the one-way barrier of the horizon. The Big Bang would then be a white hole, the outward-facing twin of a black hole, releasing energy instead of devouring it. If this is true, then our universe might exist within the event horizon of a black hole born in some parent universe. The singularity that once seemed to mark the beginning of time would instead be the bridge between one cosmos and another. To the outside, our universe would appear as a black hole, a region from which no light escapes. To us, it would appear infinite, filled with galaxies and radiation stretching as far as we can see. Both views would be correct, each from its own side of the horizon. To grasp this strange symmetry, recall that general relativity treats space-time as a four-dimensional fabric. A black hole curves this fabric so steeply that inside it, every direction points inward toward the center. But when the equations are extended beyond the singularity, when quantum gravity effects are included, the curvature can rebound, producing expansion rather than collapse. In that rebound lies the possibility of cosmic creation. The interior grows, its space inflating, while the outer universe sees only a region of darkness. Time for the outside slows near the horizon until it nearly stops, while inside, time races forward, birthing an entire universe before the external observer sees even a flicker. Mathematically, this connection emerges from comparing the Schwarzschild solution, which describes a non-rotating black hole, with the Friedmann-Lemaitre-Robertson-Walker metric that describes an expanding universe. Both are solutions to Einstein's field equations, differing only in how they distribute curvature and energy. In one, space collapses toward a singularity. In the other, it expands outward from one. The mirror symmetry is striking. It suggests that what we call the Big Bang might be the inside-out version of a black hole's birth. The concept unites several puzzles. It explains why our universe appears to have a finite age, yet no boundary. We live in a region that began with a collapse and continues as an expansion. It also explains why our cosmos has an event horizon beyond which light can never reach us. In relativity, any accelerating expansion creates such a horizon, a surface where space recedes faster than light. The observable universe, then, behaves like the interior of a black hole, whose horizon is the cosmic boundary we see. From our perspective, the horizon surrounds us in every direction, enclosing us within an expanding bubble of space-time. The physics of this idea has an eerie beauty. Outside a black hole, gravity pulls everything inward. Inside, the same equations describe expansion pushing everything apart. The difference is only a matter of which side of the horizon one occupies. If our universe is indeed the inside of such a structure, then what we call cosmic expansion is the continuation of a collapse that began elsewhere. The stars, galaxies, and even the vacuum between them are the unfolding of that process, a transformation of infalling matter into an expanding cosmos. Some versions of this theory draw on the concept of cosmic bounce, where quantum effects prevent the final singularity from forming. When the density of matter becomes extreme, quantum pressure counters gravity, causing a rebound. The energy released in that rebound could seed a new universe. From the parent universe's perspective, the black hole remains small and silent. From the inside, an entire cosmos bursts into being. This perspective redefines the meaning of inside and outside. If every black hole births a new universe, then our own cosmos might contain countless others within it. Each black hole we observe could be a gateway, a womb of space-time gestating new worlds beyond our perception. The multiverse, in this sense, is not a parallel collection of universes floating side by side, but a chain of nested realities, each born from the death of a star in the one before it. And what about time? Inside a black hole, time and space exchange roles. The singularity becomes a temporal boundary, not a spatial one. The direction inward is the direction forward in time. That means that for us, living inside such a structure, the future points away from the singularity, the moment of our Big Bang. Every second that passes carries us farther from that origin, deeper into expansion. From the outside, however, the process appears frozen. To an external observer, nothing ever crosses the event horizon. Matter falls in and seems to stop at its edge, time halted by gravity. To us, time flows naturally. To them, it stands still. Both views are true, each defined by its own geometry of time. If the universe truly exists inside a black hole, then the boundary between existence and nothingness is not a wall, but a horizon of perspective. The outside world, if it exists at all, can never communicate with us. Our entire reality would be sealed off by the very physics that sustains it. From inside, space appears infinite. From outside, it appears infinitesimal. The two descriptions coexist, like different faces of the same equation. And so the possibility emerges that the cosmos we call home is itself the interior of a colossal gravitational object, a region where time is expanding outward instead of collapsing inward. The Big Bang was not the beginning, but a transition, a moment when another universe's death gave birth to our own. Inside a black hole, time and space lose their familiar meanings. What appears from the outside as a point of infinite collapse may, from within, be the origin of a vast and expanding cosmos. To understand this inversion, imagine falling toward a black hole's event horizon. To a distant observer, your descent slows as you approach the boundary, your signals stretching longer and fainter until they fade completely. But from your own perspective, nothing strange happens. You cross the horizon smoothly, unaware of any boundary at all. Space seems to open up, not close down. You continue inward, though inward now behaves like forward in time. The horizon is not a wall, it is a turning of geometry, where the meaning of direction changes. In that reversal lies a profound symmetry. The outside universe, where gravity pulls inward, and the inside universe, where expansion pushes outward, are reflections of each other. In the equations, the transformation is simple. What collapses in one coordinate frame expands in another. If quantum gravity prevents the singularity at the center from becoming infinite, the collapsing matter rebounds, inflating a new space-time. This is the essence of the black hole cosmology, the idea that each black hole births a new universe on the other side of its horizon. If our universe formed this way, the Big Bang was not a creation from nothing, but the continuation of a process already in motion. Somewhere, in a parent cosmos, a massive star or perhaps an entire region collapsed beyond its event horizon. The energy and curvature within that collapse reached conditions so extreme that space-time split, forming a new domain where expansion replaced contraction. We live within that rebound, looking outward from the inside of the horizon, unaware that the surface we call the cosmic boundary once marked the edge of another universe's collapse. Such a model carries both elegance and disquiet. It replaces metaphysical creation with physical transformation, yet it also traps us inside a cosmic isolation chamber. No signal can escape our universe's horizon to reach the parent cosmos, and no signal from that parent can reach us. Information from before the Big Bang is erased, not by destruction, but by separation. The laws of relativity make the barrier absolute. We are cut off from our origin, not by distance, but by geometry. This isolation explains why the universe appears homogeneous and isotropic on large scales. Every observer inside an expanding black hole universe would see themselves at the center of an isotropic cosmos, surrounded by horizons in every direction. The Copernican principle, rather than being violated, is preserved by relativity itself. Each observer perceives the same expansion because the geometry of space ensures it. No one can see beyond the horizon to tell where the true center lies. There is no preferred location because the horizon hides all others. Physicists who study these models use equations drawn from both cosmology and black hole physics. The Friedmann equations describe the expansion of the universe, relating its curvature, energy density, and scale factor. The Schwarzschild metric describes the space-time around a black hole. When these are joined under certain boundary conditions, one can morph continuously into the other. The parameters differ, mass, density, and scale, but the underlying curvature behaves identically. The apparent difference between a black hole interior and a universe like ours is one of interpretation. The same mathematical fabric can describe both collapse and creation. If every black hole can become a universe, then perhaps the number of universes is beyond counting. Each black hole in our cosmos could be the seed of another, its interior expanding in its own flow of time, hidden behind an event horizon that, from our side, looks like an end. The mass of the parent black hole would determine the properties of its offspring universe, the strength of its gravity, the density of its matter, perhaps even the values of its fundamental constants. A chain of universes would emerge, each generation born from the gravitational death of the last. The multiverse would not be a collection of parallel worlds floating side by side, but a recursive lineage, each universe contained within the black holes of another. In such a scenario, time itself becomes a kind of evolutionary ladder. Universes give birth through collapse, passing their physical constants forward like genetic traits. Small variations might determine whether a universe lasts long enough to form galaxies, stars, and life. Those with stable conditions produce many black holes, which in turn create many offspring. Over countless generations, universes that favor black hole formation become dominant. It is a cosmic natural selection, written not in biology, but in gravity. The fact that our universe is filled with black holes might then be no coincidence. It could be the mark of a long ancestry shaped by gravitational fertility. But these are speculations built upon solid mathematics. The observational evidence is subtle and indirect. The similarity between the equations of cosmic expansion and black hole interiors does not prove identity, yet it invites curiosity. Some signatures could betray our black hole origin. For instance, the apparent flatness of the universe, the way its geometry balances on the knife edge between open and closed, could arise naturally inside a large black hole. Likewise, the finite age and the existence of a cosmic horizon echo the properties of an interior bounded by an event horizon. Even the distribution of energy in the cosmos, dominated by dark matter and dark energy, might reflect the initial conditions inherited from the parent collapse. What would it mean to accept this picture? It would mean that our cosmos is both infinite and finite at once. Infinite from the inside, because space stretches without bound as it expands. Finite from the outside, because it is enclosed by its horizon. It would mean that creation is not a single event, but an ongoing process, with each universe spawning others through the language of gravity. And it would mean that everything we see, the galaxies, the stars, the empty space between them, is part of a transformation that began long before our own beginning. Such a realization changes how we see existence itself. The darkness between galaxies becomes not a void, but the depth of an interior space. The cosmic horizon becomes not the edge of the universe, but its skin, and the singularity, that mysterious origin of all things, becomes not a point of infinite density, but a bridge between worlds. If our universe truly lies inside a black hole, then everything we call reality, the galaxies, the cosmic web, even the flow of time, is the unfolding of that interior geometry. What began as collapse in one world becomes expansion in another. To the parent universe, our cosmos is no larger than the event horizon that encloses it, a sphere of finite size. To us, inside, space seems unbounded, stretching forever. This duality is not illusion. It is how space-time behaves when curvature becomes extreme. Inside such a structure, gravity does not pull things together as it does outside. Instead, the fabric of space expands in every direction. What we interpret as the cosmic acceleration might simply be the continuation of that interior growth. The horizon surrounding our universe would be the black hole's boundary, and its radius would define the observable universe. Beyond it lies the region where light can never return, the interface between our reality and the unknown. In this picture, the Big Bang was the moment when the interior of the black hole began to expand. The temperature and density then were unimaginably high, not because matter appeared from nowhere, but because it was compressed during the collapse that formed the black hole. The energy released during that transition would drive inflation, the rapid exponential expansion that smoothed out irregularities and created the uniform cosmos we see today. In this way, inflation becomes not an arbitrary feature of cosmology, but a natural consequence of the black hole's rebound. From the perspective of general relativity, this process is entirely symmetrical. The equations that describe the gravitational collapse of matter can also describe its reverse, an expansion governed by the same rules, but unfolding in a different direction of time. What we call the arrow of time inside the universe points outward from the singularity because that is the direction of increasing entropy, just as the arrow of time outside the black hole points toward its center. The two flows are mirror images, each seeing the other as running backward. To the parent universe, our Big Bang was the instant matter vanished into darkness. To us, it was the instant light was born. The boundary separating these realities is the event horizon. From inside, it appears as the cosmic horizon beyond which we can never see. Light emitted from beyond that surface will never reach us, because space there recedes faster than light can travel. To an external observer, nothing ever crosses that boundary. Objects falling toward it slow down and freeze in time. The black hole's growth appears to stop. Yet inside, time flows freely, and the universe continues to evolve. What seems frozen from one perspective is alive and expanding from another. This inversion of time and perspective gives rise to the most haunting implication of all, that the distinction between inside and outside is relative. A universe inside a black hole might itself contain black holes that spawn new universes, each layer repeating the pattern endlessly. In this nested structure, reality has no absolute beginning or end, only transitions, each hidden behind a horizon. The birth of one universe is the death of another, the heartbeat of an infinite chain of creation and collapse. Physicists have begun to explore whether quantum mechanics supports this picture. In classical relativity, information that falls into a black hole is lost forever, but quantum theory forbids such loss. The information paradox, one of the greatest puzzles in modern physics, might find resolution if the interior of a black hole evolves into a new universe. In that case, information is not destroyed, but transferred, encoded in the initial conditions of the child universe. The horizon acts as a membrane, preserving the total information content even as it hides it from view. This connection between horizons, information, and entropy leads naturally to the holographic principle, the idea that everything inside a region of space can be described by information encoded on its boundary. If our universe exists within a black hole, then everything we experience could be the three-dimensional projection of data inscribed on its horizon. Reality itself would be holographic, its true nature existing not within, but on the surface that separates us from the outside. Our galaxies, stars, and lives would be patterns written in the faint glow of a cosmic event horizon. Such a vision blurs the line between physics and philosophy. The black hole universe hypothesis suggests that existence is recursive, that every horizon hides another reality within. What we call the universe may be one iteration in an infinite sequence of births and deaths, each generation preserving the essence of the last through curvature and information. The cosmos would then be eternal, not in time, but in process, its self-replication the only constant. From our vantage point, sealed inside this gravitational womb, we cannot confirm the existence of the parent universe. The horizon ensures our isolation. Yet the echoes of that origin may still linger in the background radiation, the faint anisotropies of the cosmic microwave background that record the initial conditions of our birth. Perhaps, buried in those ripples, lies the signature of the collapse that gave rise to us, a fingerprint from a dying world. If so, then the stars above are not just distant suns, but memories of another universe's ending. The matter that formed them once belonged to a world that collapsed long ago, its light extinguished, its time reversed. We are the continuation of that story, living on the inside of its shadow. The cosmos we see expanding around us is the unfolding of its final breath. The realization is both humbling and exhilarating. We are not outside the universe looking in. We are inside a gravitational miracle, part of a sequence so vast it defies imagination. The event horizon we can never cross is not a prison, but a cradle, holding within it the growth of everything we know. Beyond it, perhaps, another universe waits to be born from one of our own collapsing stars, continuing the eternal rhythm of creation through gravity's hand. Light is the universe's storyteller. It carries every record of cosmic history, every trace of what has been. Yet light does not move freely. It is bent, slowed, and stretched by the geometry of space-time. In a universe made of curves, no path is truly straight. Every photon we observe has crossed invisible valleys of gravity and climbed unseen hills of emptiness. What we call reality is a projection of these distorted journeys, an image shaped by the universe's lens. Einstein predicted this in 1915 when he showed that gravity is not a force, but the bending of space-time. Massive objects curve the geometry around them, and light follows that curve. When starlight passes near a massive cluster of galaxies, its path bends, and the image we see is magnified, stretched, or multiplied. This phenomenon, gravitational lensing, transforms the universe into an optical illusion. The sky we see is not a window, but a mirage. Every galaxy's light is subtly deflected by the mass it encounters, its shape and brightness rewritten before it reaches our eyes. On smaller scales, lensing acts like a natural telescope, revealing galaxies too faint to be seen otherwise. On the larger scales, it alters our perception of distance, age, and speed. In an expanding universe filled with voids and filaments, the light from distant sources is constantly redirected, creating a complex map of apparent motion. Galaxies may seem farther or faster than they truly are, because their light has taken a longer, more twisted path through warped space. Even time itself can be delayed or duplicated. A single supernova, lensed by a cluster, might appear multiple times across the sky, each image arriving at a different moment, because space-time between them is not flat, but folded. If our universe is a bubble or the interior of a black hole, the entire cosmic stage becomes a gravitational lens. The curvature of space-time across our bubble would shape how light travels on its way to us, making distant regions appear accelerated, stretched, or curved. What we interpret as cosmic expansion might partly be an optical effect, a vast lensing of reality caused by the geometry of the universe itself. We look out at galaxies receding into the dark, but perhaps what we are truly seeing is light distorted by the curvature of our own cosmic cavity. Inside this curvature, even emptiness acts like a lens. Voids, those immense underdense regions that dominate cosmic volume, bend light in reverse. Instead of focusing like a magnifying glass, they defocus, stretching images and dimming them slightly. When light travels through a void, its wavelength grows, redshifting more than expected. The difference is tiny, but cumulative across billions of light years. In a universe filled with thousands of voids, the cumulative lensing of emptiness could mimic an overall acceleration. Space itself, acting as a field of diverging lenses, might trick us into believing that galaxies rush away faster than they do. Some cosmologists have begun to test this idea with deep surveys of gravitational lensing patterns. By mapping how light from distant quasars and galaxies is distorted across the sky, they can reconstruct the three-dimensional distribution of mass. These maps reveal that the universe's curvature is not uniform, but lumpy, with alternating regions of focus and defocus. Each acts as a lens whose combined effects blur our view of the cosmos. The pattern resembles a vast optical interference, as if reality itself was seen through an imperfect glass. In such a cosmos, even the concept of distance becomes slippery. The brightness of a galaxy depends not only on how far its light has traveled, but on how space-time has warped along the way. Two galaxies at identical true distances could appear vastly different in brightness or redshift if the geometry between them differs. The universe, in this sense, is a hall of mirrors, each photon tracing a unique, distorted path through the corridors of gravity. Gravitational lensing also alters time. When light passes through regions of strong curvature, the clock that measures its journey slows. This effect, known as the Shapiro delay, means that light can take longer to arrive than it would in flat space. A beam passing near a massive cluster of galaxies might be delayed by thousands of years. Across cosmic distances, such delays accumulate, bending not only our sense of space, but our sense of when events occur. The universe we see at any moment is therefore not just distant in space, but uneven in time. A mosaic of epochs stitched together by gravitational distortion. If we live inside a black hole or a cosmic void, these distortions could define our entire perception of the universe. Light from the farthest galaxies travels through the expanding curvature of our bubble, its energy diluted, its wavelength stretched. To us, those galaxies appear to accelerate away, but they might simply be embedded in a space-time that acts as a universal lens. In this view, the cosmic horizon, the farthest distance we can observe, is not a limit of existence, but the optical boundary of our own whole. Beyond it, light cannot reach us, not because there is nothing there, but because the geometry forbids it. Such a perspective reshapes even the meaning of observation. When astronomers measure redshift, luminosity, and distance, they are decoding not the universe itself, but its projection through space-time's lens. Every chart of cosmic expansion, every map of the large-scale structure, is an image seen through curvature. The cosmos we know is therefore both real and illusionary. Real in its local physics, illusionary in its appearance across vast distances. The lens does not deceive maliciously, it simply follows the laws of gravity. To peer into the universe is to look through layers of distortion accumulated across billions of years. The faint glow of the cosmic microwave background, the oldest light we can see, is itself lensed by everything between then and now. Its smoothness, its tiny ripples, all carry the fingerprints of intervening mass and voids. By studying those distortions, scientists can measure the total curvature of space-time within our observable bubble. They find that it is nearly flat, but nearly may be the most deceptive word in cosmology. Even the smallest deviation from perfect flatness, stretched across billions of light-years, could signify that we inhabit a curved cavity, a lens whose focus is so vast we cannot perceive its edges. And so, when we look to the stars, we are not seeing the universe as it is, but as curvature allows it to be seen. The night sky is a lens, and we are its prisoners and its beneficiaries. Every point of light has been bent by unseen hands, every shadow a projection of geometry. Reality itself is a pattern of refraction through space-time's invisible glass. Light does not tell the truth directly. It tells the truth through curvature, through the long detours it must take to reach us. A photon that leaves a distant galaxy does not travel straight across an empty void. It bends around the invisible contours of gravity, passing through fields of mass and rivers of expanding space. When it finally reaches our telescopes, the message it carries has been stretched and altered, its color shifted, its timing delayed. To read the universe, we must learn to interpret these distortions as part of the story, not errors in the telling. The phenomenon of gravitational lensing proves that the universe is not a passive arena where light simply moves, but an active participant that sculpts the path of every beam. In the deepest sense, this means our view of the cosmos is not a direct image, but a reconstruction, an inference drawn from how light is shaped by the geometry it crosses. When astronomers assemble maps of galaxies, clusters, and voids, they are really mapping how space bends. Every observation of the heavens is a record of curvature. Even the most distant light we see, the afterglow of the Big Bang, reaches us through this lens. The cosmic microwave background is a tapestry of tiny temperature variations, ripples imprinted when the universe was less than 400,000 years old. But those ripples have been subtly distorted by everything that has happened since. As the ancient radiation traversed billions of light years, its pattern was bent by the gravitational fields of intervening structures. The result is that what we call the oldest picture of the universe is not pristine at all. It is filtered through eons of cosmic lensing. To truly understand the beginning, we must untangle this web of distortions woven by gravity itself. When the light from faraway quasars passes near clusters of galaxies, it can form multiple images. Sometimes those images appear on opposite sides of the cluster, sometimes as rings of light known as Einstein rings. Each image arrives at a slightly different time because the path of light through warped space is longer or shorter depending on the curvature. In one famous case, astronomers watched the same supernova explode several times, each flash arriving years apart, as the light followed alternate routes through the lensing cluster. Time in these cases behaves like glass, transparent yet uneven, bending both space and sequence. This effect is not confined to rare alignments. Every particle of light from every distant object has been lensed to some degree. Even the gentle expansion of space acts as a universal lens, stretching wavelengths and making light redder the farther it travels. We call this cosmic redshift, and we use it to measure distance and velocity. But the assumption that redshift corresponds directly to expansion may be too simple. If the geometry of the universe itself changes across large regions, if we live inside a cosmic bubble or near the center of a vast void, then part of the redshift we see could come from gravitational curvature rather than universal acceleration. Light leaving denser regions loses energy as it climbs the gravitational slope toward emptier space. The result mimics the effect of a universe speeding up. To test this possibility, astronomers use cosmic shear, the tiny distortions in the shapes of distant galaxies caused by weak lensing. By studying how galaxy images are stretched across the sky, scientists can infer how mass is distributed and how space-time itself is curved. The data show that voids indeed act as divergent lenses, spreading light outward and slightly dimming distant objects. The effect is small, but across billions of light-years it accumulates. The collective lensing of many voids can alter how we perceive cosmic expansion, shifting the apparent brightness of supernovae and subtly changing the inferred geometry of the cosmos. Even our measurement of the Hubble constant depends on these effects. When we measure distances using standard candles, objects of known brightness such as Type 1 are supernovae, we assume their light travels through uniform space. But in reality, the light passes through a patchwork of density variations, some focusing, some defocusing. These small biases could help explain why measurements of the Hubble constant differ depending on whether they come from the nearby universe or from the early cosmic microwave background. Geometry and gravity combine to play tricks on our cosmic ruler. Lensing also defines the horizon of what can be known. Beyond a certain distance, the curvature of space grows so severe that light cannot reach us. This limit, the cosmic horizon, is analogous to the event horizon of a black hole. In both cases, light emitted beyond the boundary is forever out of reach. The difference is that in a black hole, the curvature is caused by collapse, while in our universe, it may be caused by expansion. Yet mathematically, the two are almost identical. The cosmic horizon is a lens of infinite power, bending light so completely that information from beyond it can never arrive. To us, it is the edge of existence. To the equations, it is simply where geometry folds back on itself. To stand on a planet orbiting an ordinary star and realize that the sky above is a lens of space-time is an act of both science and humility. We are not seeing the universe as it truly is. We are seeing its projection through gravity's glass. Even the empty dark between galaxies is not truly empty, but filled with the invisible mass that shapes every beam of light. The universe paints its portrait not with color, but with curvature, and we are the observers inside that painting, trying to read the brushstrokes from within. If our cosmos is indeed a bubble or the interior of a black hole, then every photon that reaches us has been curved by that structure. The image we call the universe is an inside-out reflection of the geometry we inhabit. The stars are not scattered randomly, but arranged by the paths light is allowed to take. What we call expansion may be the optical manifestation of curvature, the bending of time and distance on scales so vast that the distinction between reality and appearance disappears. Perhaps that is why the universe seems both infinite and finite at once. The lens through which we view it stretches space without end, yet the horizon that defines that lens encloses everything we can ever know. We live inside the ultimate optical illusion, a self-contained projection of space-time, where inside and outside, near and far, are different expressions of the same curve. The bending of light does more than distort. It defines what reality even means from within a curved universe. Imagine a single photon born in the violent core of a distant quasar, billions of light years away. Its path to us is a voyage across expanding space, through rivers of gravity and valleys of voids, each with its own subtle curvature. By the time that photon reaches our detectors, it has aged across cosmic time, its wavelength stretched into red by expansion, its direction twisted by unseen hands. We receive it and believe we are observing the universe directly. But what we truly see is the geometry that the photon has crossed. Our universe, then, is not a flat window, but a sphere of lenses layered upon lenses. Every galaxy cluster, every filament of dark matter, every void acts as a lens, warping and re-warping the light that travels through it. The entire observable cosmos is the sum of those distortions, a curved projection on the inside surface of our cosmic bubble. When astronomers reconstruct images of the deep sky, they are in fact reversing billions of years of gravitational sculpting, decoding the optical memory of space-time itself. And this lensing does not only bend light, it bends time. When light curves through a gravitational potential, it experiences time differently. Near massive bodies, time slows. Across voids, it speeds. Each photon carries that history. When we receive light from distant epochs, we see not just the structure of the universe, but its temporal topology, the uneven flow of time across vast distances. What looks like an expanding universe may be, in part, an illusion caused by the differential ticking of cosmic clocks. The deeper we look, the more the universe behaves like a self-referential mirror. The geometry that defines how we see is itself invisible, inferred only from its distortions of light. It is as if reality hides its own structure behind its reflection. When we map galaxies, we are really mapping the invisible scaffolding of gravity, the unseen filaments of dark matter that dictate where galaxies can exist. Those filaments form the skeleton of the cosmic web, but the web itself is a lens, a vast structure bending space-time in ways that shape the very patterns we observe. This interplay between gravity and perception raises a haunting possibility. Perhaps there is no objective image of the universe at all. Every observation depends on the path light takes to reach us, and that path depends on the curvature it crosses. Two observers in different parts of the universe might see entirely different cosmic histories, not because the universe differs for them, but because the geometry around them reshapes what they can see. There may be no single view of the cosmos, only local truths filtered through curvature. Inside a cosmic bubble, this becomes especially profound. The interior curvature defines how light behaves across the entire visible universe. Rays from distant galaxies curve inward as they climb through the gradient of expansion, making the outer cosmos appear accelerated. The farther light travels, the more stretched its wavelength becomes. Not because the universe speeds up, but because the geometry amplifies the illusion of motion. We interpret this as dark energy, a mysterious force pushing galaxies apart. Yet it may simply be the optical signature of our cosmic lens. Consider the horizon we call the edge of the observable universe. From our point of view, it is a surface of last light, the farthest distance from which photons can reach us. But from a geometric perspective, it is a caustic, a focus point of space-time curvature, where light paths converge and diverge infinitely. Beyond it, light bends so sharply that it never returns. In relativity, such horizons always mark limits of perception, not necessarily limits of existence. The universe may continue beyond our horizon, but we can never know. The lens that defines our cosmos also defines its boundary. The same principle holds for black holes. Their event horizons are not walls, but optical boundaries where curvature bends light so completely that outward paths become inward. Our cosmic horizon behaves similarly, but on a grander scale. If our universe is the interior of a black hole, then what we see as cosmic acceleration is the result of light curving through the geometry of that interior. The entire sky becomes a lens through which we view the inside of an event horizon from within. To live inside such a lens is to exist within an illusion that is nonetheless real. Every particle, every photon, every second we experience is shaped by curvature. Yet that curvature is what gives the universe its structure and its meaning. The distinction between appearance and reality fades because the lens is not separate from the world. It is the world. Space and time are the medium through which all perception passes, and they are never flat. When you gaze at the night sky and see a galaxy whose light has traveled for billions of years, you are not looking outward across space. You are looking backward through layers of curvature, across the folds of a lens that contains you. The stars do not mark distant places, they mark the shape of the universe you inhabit. The cosmos you perceive is a projection, but a projection that defines your existence. We think of ourselves as observers of the universe, but perhaps it is more accurate to say that the universe observes itself through us, using light and curvature as its mirror. Every photon that reaches our eyes has followed a path carved by gravity. Every reflection, a conversation between matter and geometry. In that sense, perception is cosmic, an interaction between the smallest particles of light and the largest scales of existence. When viewed this way, the universe becomes both elegant and unsettling. If light and curvature together create the illusion of expansion, then our sense of cosmic destiny is not written in energy, but in geometry. We might not be watching galaxies rush away into endless darkness. We might be watching light fall through the lens of the hole we live in. The cosmos, in its grandeur, could be a single, continuous optical illusion, and we are the creatures living inside its projection. Every cosmological theory hides a secret fear, that we might once again be at the center of everything. The Copernican revolution freed humanity from that vanity, teaching us that Earth circles the sun, that the sun drifts through the galaxy, and that our galaxy is just one island among trillions. But the idea of a cosmic void, a bubble with us near its middle, seems to threaten that hard-won humility. If the universe looks the way it does because we occupy a special place within it, have we returned to the center after all? The answer lies in relativity itself, which erases the very notion of a single center. In a curved space-time, every observer can consider themselves at the origin, because geometry expands uniformly from every point inside. A balloon has a center in three-dimensional space, but to creatures living on its two-dimensional surface, no location is special. Every point sees the universe stretching away equally in all directions. The same is true of our three-dimensional cosmos. Even if we live inside an enormous void, every observer within it would see galaxies receding symmetrically. The illusion of centrality would be universal. This is the essence of the centerless illusion. The laws of physics guarantee that we cannot determine an absolute position in the cosmos. There is no fixed frame, no privileged viewpoint. The light that reaches us carries information shaped by curvature, but not by absolute placement. Every observer inside a cosmic bubble experiences the same apparent acceleration, the same geometry of horizons. It is not that we are at the center, it is that there is no center at all. When Subir Sarkar at Oxford and David Wiltshire in New Zealand modeled the universe as a vast, underdense region, billions of light years across, they showed that such a configuration could reproduce the observed patterns of supernova redshifts and cosmic microwave background data without invoking dark energy. Their models demonstrated how curvature and differential time flow within an inhomogeneous universe can mimic acceleration. Inside a void, time runs faster than in denser regions. Clocks farther out tick more slowly, and light from them appears redder and older. The result is a self-consistent illusion. To everyone inside, it looks as if space is expanding faster the farther one looks. The cosmic microwave background adds another layer to this illusion. It surrounds us evenly, a faint bath of ancient light left over from the universe's early fire. Its near-perfect isotropy is one of cosmology's greatest triumphs, showing that the cosmos is remarkably uniform on large scales. But even slight anisotropies, the tiny differences in temperature across the sky, could carry traces of the void structure that envelops us. If our region of space expands a little faster than average, then photons arriving from one direction would be redshifted slightly more than from another, introducing small but measurable patterns. Observers anywhere inside the void would see similar effects, preserving the illusion of uniformity. In this way, the universe becomes self-similar. Each region believes itself typical because local physics remains consistent. The curvature of space-time hides the global geometry behind perfect local order. The Copernican principle survives, but it does so through relativity rather than simplicity. We are not central. We are simply embedded in a structure that makes every place appear central. Yet this realization invites a deeper unease. If there is no center, there may also be no boundary, no absolute measure of what the universe truly is. All distances, times, and scales become relational, defined only by the geometry that connects them. The universe might have infinite volume from our perspective, while being finite in total curvature, just as the interior of a black hole can appear endless to those within it. In such a cosmos, meaning and position dissolve together. The universe does not expand into anything. It expands within itself, and we expand with it. The centerless illusion also reshapes how we think about time. If our cosmic bubble expands faster near its interior, then the flow of time itself is not uniform. The further outward one goes, the slower cosmic clocks tick relative to ours. The past we observe in distant galaxies is not only their history, but a slower slice of time altogether. Their now is not our now. This temporal relativity ensures that no universal present exists, only overlapping layers of time, each flowing at its own pace according to curvature. The illusion of simultaneity dies with the illusion of centrality. In this strange geometry, even the idea of expansion takes on new meaning. We think of galaxies moving through space, but in truth, it is space itself that grows between them. If space-time is curved inward like a lens, that growth is perspective dependent. Each observer sees all others receding, yet none feels motion themselves. The universe thus expands without a center of expansion, without an external space into which it grows. It is pure geometry unfolding, an eternal blossom with no seed and no edge. Cosmologists continue to test whether this illusion holds true. The next generation of surveys, Euclid, the Vera Rubin Observatory, and the Nancy Grace Roman Space Telescope, will map billions of galaxies, tracing their redshifts and clustering across the sky. By comparing these patterns with predictions from both the dark energy model and the void model, scientists hope to determine whether cosmic acceleration is genuine or geometric. But the truth may defy both frameworks. Perhaps dark energy and geometry are two ways of describing the same thing. The evolving curvature of a space-time that has no center, no boundary, and no external reference. If that is the case, then the universe we perceive is not an expanding object, but a self-referential illusion sustained by its own geometry. Every horizon is a reflection of the observer, every measure of time a product of the curvature that defines their world. We are not at the center of the universe, nor are we lost within it. The center is everywhere, and the illusion is everything. There is a line that separates what we can see from what we can never see, a silent boundary drawn not by distance but by time. Cosmologists call it the cosmic horizon, the limit beyond which light has not had enough time to reach us since the universe began. It is not a physical wall. It is a boundary written into the fabric of space-time itself, a limit defined by the speed of light and the expansion of the universe. Everything beyond it exists, perhaps, but will remain forever invisible. The horizon is where the story of the cosmos fades into the unknown. In relativity, this boundary behaves in a way eerily similar to the event horizon of a black hole. Both are places where space stretches faster than light can cross. Both isolate observers from what lies beyond. To those outside a black hole, the horizon is a veil from which nothing escapes. To us, inside the universe, the cosmic horizon is a veil we cannot pierce. Light emitted from beyond it will never reach us, because space between us and that light expands too quickly. The distance grows faster than the photon can travel. It is a mirror of limits, one internal, one external, yet governed by the same laws. At roughly 46 billion light-years in every direction, the cosmic horizon defines the observable universe. Everything we can see fits within that sphere, and everything outside is cut off not by emptiness, but by the speed of expansion itself. In a universe that accelerates, that horizon will eventually shrink in practical terms, because more and more galaxies will slip beyond it as time passes. Their light will fade, their signals redshift into oblivion, until the cosmos appears empty. The night sky of the far future will contain only the ghostly remnants of our own local group of galaxies, the rest swallowed by the horizon of nothingness. It is a haunting thought that the vast richness of the universe, the galaxies and nebulae that fill our telescopes today, are temporary features of visibility. The cosmos is not fading because it dies, but because it outruns its own light. Expansion is not a movement through space, but a stretching of space itself. Every second, new regions cross the threshold beyond which communication is impossible. The universe is both infinite in potential and finite in experience. From the perspective of general relativity, this horizon behaves exactly like a black hole's event horizon, only inverted. To an observer outside a black hole, time slows near the horizon until it stops. To an observer inside an accelerating universe, time beyond the horizon moves infinitely fast. In both cases, the boundary marks a division between accessible and inaccessible regions of space-time. The symmetry is profound. The interior of a black hole and the interior of our universe are mathematically reflections of each other. Imagine standing near the event horizon of a black hole, watching the last flicker of light from a falling star. The light slows, reddens, and fades, never quite vanishing, but never crossing the boundary in your view. Now imagine an observer in another universe, watching us from beyond our cosmic horizon, if such a vantage existed. To them, our entire universe would appear to freeze at its edge, time halted by the expansion that defines it. From outside, we would seem motionless. From inside, we would see time flow forward normally. Each frame of reference is valid, yet neither can see the other's truth. This duality raises a question that sits at the edge of physics and philosophy. If horizons define what can be known, do they also define what exists? When we say that light from beyond the horizon can never reach us, are we describing a limitation of perception or a limitation of reality itself? In quantum field theory, horizons have temperature. A black hole radiates faintly due to quantum fluctuations near its event horizon, a process known as Hawking radiation. By analogy, our cosmic horizon should also radiate, bathing the universe in a faint glow of thermal energy. That glow may be indistinguishable from the cosmic microwave background, the relic heat of the Big Bang. If so, then the horizon is not an empty edge, but a living surface, a membrane through which the universe exchanges information with the unknown. The physics of such horizons suggests that the boundary between being and nothingness is never sharp. Information may be conserved, encoded on the surface of the horizon itself. The holographic principle tells us that everything we can observe within the universe can be described by data inscribed on its boundary. If that is true, then the horizon of nothingness is not where the universe ends. It is where its meaning resides. The cosmos may be a projection from this boundary, an interior woven from the information that the horizon holds. To live within a universe that has such a boundary is to live within a paradox. From our perspective, the horizon is unimaginably far, yet it defines every observable property of space and time. Its temperature, its curvature, its slow retreat into invisibility, all determine how galaxies evolve and how light travels. It is the silent architect of cosmic history, shaping reality from the edge. The nothingness beyond it is not a void, but a region forever beyond reach, perhaps another domain, perhaps simply beyond definition. When physicists calculate the fate of the universe under continuous acceleration, the result is chillingly elegant. As expansion continues, galaxies will vanish one by one beyond the horizon. Star formation will cease, black holes will evaporate over unimaginable timescales, and the cosmic temperature will approach absolute zero. Eventually, even the photons that carry the last traces of light will stretch so thin that their energy becomes meaningless. The universe will flatten into darkness, a vast, cold equilibrium where time itself loses definition. From our viewpoint, that is the end. From another perspective, perhaps it is the beginning of another interior somewhere beyond the horizon. The horizon of nothingness is therefore both a boundary and a promise. It reminds us that the universe we know is finite in what it can reveal, yet infinite in what it can imply. Beyond it lies not emptiness, but continuation, unseen and unreachable, governed by the same equations that shape our own existence. The horizon is the line between knowing and being, between the universe we inhabit and the universes we can only imagine. Time is not an external clock ticking over the universe. It is woven into the very structure of space, stretched and compressed by gravity, warped by motion and shaped by density. In Einstein's vision, there is no absolute flow, only relative motion through a four-dimensional fabric called space-time. Every region of the cosmos has its own rhythm, determined by how gravity curves the geometry around it. Inside massive clusters of galaxies, where matter is dense, time runs slightly slower. Inside vast cosmic voids, where matter is scarce and space expands more freely, time runs faster. This difference, though small, changes everything. Over the age of the universe, a difference of only a few billionths in the rate of cosmic clocks can accumulate into measurable distortions. Observers inside a large underdense region like the local void could experience the passage of cosmic time more quickly than those in denser regions. Their galaxies would age faster, their supernovae would appear dimmer, and their measurements of expansion would show acceleration. The effect would be subtle, invisible to the senses, yet powerful enough to reshape our understanding of cosmic evolution. In such a universe, the shape of time mirrors the shape of gravity. Imagine a cosmic map, not of stars or galaxies, but of the ticking of clocks. Each point in space has its own pace of time, determined by local curvature. The result is a landscape of temporal hills and valleys, where gravity pulls on the flow of time as surely as it pulls on matter. Deep in the wells of galaxy clusters, time slows, clinging to mass. In the broad plains of cosmic voids, it stretches, flowing more freely. We exist within one of those faster regions, and because of that, the cosmos appears to accelerate around us. Einstein's field equations allow this naturally. They relate the curvature of space-time to the energy and momentum within it. In regions where density varies, curvature varies too, and therefore time itself cannot flow uniformly. The Lemaitre-Tolman-Bondi models describe these inhomogeneous solutions, showing how observers in different parts of a non-uniform universe measure different cosmic histories. The laws of physics remain the same everywhere, but their outcomes depend on the geometry that surrounds them. This interplay between time and curvature might explain one of the deepest tensions in modern cosmology: the difference between local and cosmic measurements of the universe's expansion rate. Locally, using nearby galaxies and supernovae, we find a faster expansion. Globally, using the cosmic microwave background, we find a slower one. The discrepancy, known as the Hubble tension, could be a symptom of living inside a void where time runs slightly faster. To us, the universe seems to expand more quickly because our clocks tick more rapidly relative to the cosmic average. The consequences reach beyond mere measurement. If time flows differently in different regions, then the universe does not have a single age. Our estimate of 13.8 billion years might apply only to our region of space-time. Beyond our void, Where matter is denser and clocks tick slower, the universe might be younger. In this sense, age is a local property, not a universal constant. Cosmic time becomes relative, a mosaic of epochs stitched together by curvature. Gravity and time are two faces of the same phenomenon. To fall into a gravitational well is to move into slower time. To rise into emptiness is to move into faster time. The voids that fill most of the universe are therefore not merely empty, they are temporal plateaus, regions where the universe evolves more quickly. They are the accelerators of cosmic time. Our existence within one could mean that we experience a slightly older universe than the average observer elsewhere. The galaxies we see at great distances might exist in slower regions, their light delayed not only by distance, but by time's differential flow. This view dissolves the notion of a single cosmic present. There is no universal now stretching across the cosmos. What we call the present moment is a local slice through space-time, unique to our region's curvature. Somewhere far beyond the cosmic horizon, another part of the universe might still be unfolding events we consider ancient. The Big Bang, in this sense, never ended. It is still happening continuously along the boundary where time and gravity exchange roles. The universe is not a frozen history, but an ongoing creation, each region moving through its own version of time. To live in such a cosmos is to accept that every observation we make is tinted by where we stand in the gravitational landscape. We look outward and see acceleration, but perhaps what we are truly seeing is the difference in time between ourselves and the distant universe. Gravity bends not only space, but the very rhythm of existence. The cosmic hole we inhabit might therefore be more than an underdensity. It could be a region of accelerated time, a bubble where the flow of moments diverges from the rest of the universe. If time inside a void runs faster, then information and entropy behave differently as well. Processes that would take billions of years elsewhere could unfold more rapidly here. Stars might evolve faster. Galaxies might appear older than they truly are. Even our understanding of the cosmic microwave background, the faint radiation left from the early universe, might be skewed, since that light has passed through regions with different temporal rates. We are not passive observers, but participants in a geometry that sculpts time itself. The ultimate implication is that time and gravity are inseparable aspects of the same structure, the shape of the void. Our universe, or at least our region of it, may not be expanding into emptiness, but expanding through its own flow of time. The acceleration we see could be the visible expression of that deeper temporal curvature. The cosmic whole is not just a place, it is a tempo, a faster beat in the universal symphony. And if that is true, then perhaps the mystery of dark energy is not energy at all, but rhythm. The universe does not speed up because something pushes it. It speeds up because time itself is uneven. In the slow valleys of gravity, the music of creation drags. In the open plains of the void, it rushes ahead. We are the listeners caught in one fleeting measure of that eternal song, unaware that the tempo itself is what makes the cosmos dance. There is a theory, whispered at the boundaries of cosmology and relativity, that everything we know, every galaxy, every atom, every flicker of light, exists inside the event horizon of a black hole. It sounds like fiction, but the mathematics does not forbid it. In fact, the equations of general relativity suggest that the interior of a black hole could expand, forming a new region of space-time, isolated from the external universe. In this view, each black hole is a womb of creation, and our universe might be the offspring of another, born in the collapse of a parent cosmos. The idea first appeared in the early 1970s, when the physicist Pathria and later Eson and Brandenburger explored the possibility that the Big Bang could be the interior of a black hole. According to their models, the geometry inside a black hole, rather than ending in a singularity of infinite density, could continue as a new expanding universe. To an observer outside, the black hole would appear to contain a timeless void, frozen at the horizon. To those inside, it would look like an inflating cosmos, with its own flow of time and its own expanding space. The two views are mirrors of one another, different projections of the same space-time surface. The mathematics is striking. The Schwarzschild solution, which describes the geometry of a black hole, can be extended across its horizon. Inside, the radial coordinate that once measured distance becomes a measure of time. The direction we would think of as falling in becomes the flow of the future. Space expands inexorably, and the singularity at the center is not a point in space, but a moment in time. The origin from which everything flows outward. To those within, it feels exactly like living in a universe that began in a Big Bang. The difference is perspective. If our universe were born this way, then the Big Bang was not an explosion from nothing but a transformation of geometry. A white hole, the time-reversed twin of a black hole, bursting outward from the collapse of a previous world. The boundary between the two, the event horizon, acts as a membrane connecting parent and child universes. Information from the collapsing matter may be encoded there, preserved in the holographic surface that defines the horizon. In this sense, the holographic principle becomes not only a statement about information, but about ancestry. Every universe carries the genetic code of the one before, written on the skin of its birth horizon. Inside such a black hole universe, everything we observe, expansion, cosmic background radiation, the apparent flatness of space, could arise naturally from the curvature of the interior. What we call cosmic inflation, that brief moment of rapid expansion after the Big Bang, might simply be the geometric unfolding of space-time within the event horizon. As the interior grows, its curvature smooths, giving rise to the nearly uniform cosmos we see today. The laws of physics remain the same, but their scale changes. From outside, the black hole remains static. From inside, it is an ever-expanding universe. This picture resolves a number of paradoxes. It explains why the universe appears flat on large scales, why it seems to have begun in a hot, dense state, and why it has a horizon beyond which we cannot see. It also fits naturally with quantum gravity's suggestion that information is never lost. The data describing everything that falls into the parent black hole might persist as correlations in the radiation that escapes, or as encoded structure on the new universe's boundary. In either case, the act of creation conserves the essence of what came before. The universe becomes recursive, each generation born from the gravitational collapse of its predecessor. If that is true, then black holes within our own universe could themselves contain new universes inside. Every time a massive star collapses beyond its event horizon, it may seed another cosmos, expanding in a separate dimension of time. From our perspective, we see only the outer shadow, a sphere of no return. From within, a new reality unfolds. Each black hole becomes a cosmic seed, each singularity a birth. The multiverse, in this interpretation, is not a collection of parallel worlds, but a lineage, a tree of universes branching through time, each one nested within another. This recursive creation raises profound questions about causality. If our universe was born from a black hole in another, then the constants of physics we observe, the strength of gravity, the charge of the electron, the ratio of matter to radiation, might be inherited traits. A universe whose black holes are stable and prolific would spawn many offspring, while one with unstable parameters would produce few. Over cosmic generations, universes with favorable laws would dominate the lineage. This is cosmic natural selection, a form of evolution that operates across space-time itself. In such a scenario, our existence becomes a byproduct of geometry's long experiment. The laws of physics we observe are not arbitrary. They are the traits that allowed our parent universe to reproduce successfully. We are the descendants of countless cycles of gravitational birth and collapse, living inside a black hole whose exterior may belong to a cosmos long since gone. To grasp the scale of this idea is to confront the limits of imagination. Beyond our cosmic horizon lies not nothingness, but perhaps the exterior space-time of a larger universe. Beyond that, others may exist, each containing its own horizons, its own interiors, its own chain of creation. The structure of reality becomes fractal, with each universe a cell in an endless organism of space-time. The totality has no center, no edge, and no beginning, only the continuous transformation of curvature into new worlds. If we are inside a black hole, then the cosmic void we observe around us is not emptiness, but the interior of that geometry. The white galaxies are not falling apart into darkness. They are drifting outward along the expanding flow of time that defines the inside of the whole. The Big Bang was not a singular start, but the moment we cross the horizon into being. The universe is a black hole from within and a star from beyond. And so perhaps, the story of creation is the story of recursion. Each collapse births another expansion. Each death gives rise to a new beginning. The universe is not a single event, but an eternal cycle of curvature transforming into time. To ask what came before the Big Bang is to ask what lies outside the horizon, and the answer may be another universe, dreaming of its own creation. The story always ends where it began, in light, in curvature, in the mystery of why there is something instead of nothing. We have traced the universe outward, only to find ourselves turning inward. Every path of light that leaves a distant galaxy bends through space-time and returns in concept to the same truth, that the observer and the observed are inseparable. Perhaps the cosmos has never been expanding away from us, but unfolding around us, like a reflection in an infinite mirror. If we live inside a vast cosmic void, then the expansion we see is a trick of geometry. If we live inside a black hole, then time itself is the curvature we mistake for growth. Both ideas converge on a single realization. Our universe is not what it seems. The light we measure, the redshift we chart, the horizons we calculate, they may all be symptoms of living inside a bubble of space-time, a cavity where reality loops back on itself. From within, we see galaxies receding, stars forming and dying, and the cosmic microwave background glowing faintly at 2.73 degrees Kelvin. Yet all of this may be the interior echo of something larger, a resonance from a parent universe whose collapse gave birth to our own. The Big Bang, then, was not a creation from nothing, but the continuation of a greater cycle. One universe collapsing into another, one black hole flowering into a new cosmos. If so, the universe looks back at itself through us. We are the instruments by which space-time observes its own structure. Every telescope, every photon caught by a detector, every human thought about the cosmos is part of that reflection. In the equations of relativity, the observer is not separate from the observed. Measurement changes the frame, defines the coordinates, shapes what can be known. We do not stand outside the universe taking notes. We are the notes themselves, vibrating in the cosmic song. The eerie symmetry between black holes and universes suggests that nature recycles its own geometry. A black hole curves space-time so deeply that time inside becomes space, and space becomes time. An expanding universe curves in the opposite way, turning the flow of time into the stretching of space. In both cases, the boundary, the horizon, is where meaning changes sides. What is outside for? One is inside for the other. What is collapse for one is creation for the other. This symmetry implies that there is no ultimate inside or outside, only perspectives separated by curvature. Perhaps all universes are connected through these transitions, each horizon a bridge across which space-time transforms, but information endures. The total reality, if such a thing exists, might be an infinite recursion of these transformations. Black holes spawning universes, universes spawning black holes, each carrying within it the encoded imprint of the last. In that grand recursion, time itself loses its absolute meaning. Each universe has its own arrow of time, pointing outward from its own beginning. Yet across the metastructure, beginnings and endings merge into a single timeless process, the constant exchange between collapse and expansion. To us, inside our own domain, time flows forward, galaxies recede, entropy increases. From the outside, those same processes might look reversed, frozen, or cyclical. The universe, looking back at itself from another frame, might see us as we see the stars, distant, ancient, and inevitable. Philosophers once asked whether the cosmos has a purpose, whether existence moves towards something or merely persists. In this vision, purpose and persistence are the same thing. The universe endures by transforming itself, by creating new interiors through the very mechanisms of gravity and collapse. Each generation refines the conditions for complexity, for structure, for consciousness. If universes evolve through black holes, then consciousness, the ability of space-time to reflect upon itself, might not be an accident, but an emergent property of this endless recursion. We are not separate from it. We are its awareness. Perhaps that is why we can comprehend the universe at all. The equations we derive, the constants we measure, the beauty we perceive. These are not arbitrary coincidences, but reflections of the geometry that birthed us. To understand the cosmos is to remember it. Every insight is the universe recognizing its own pattern, light folding back upon itself in the shape of thought. When we ask, what is beyond the horizon? The question itself is part of the answer. The horizon exists because we can imagine what lies beyond it. In the end, maybe there is no boundary between the scientific and the existential. The same mathematics that describes black holes and cosmic expansion also describes the limits of knowledge and perception. The curvature that bends light also bends meaning. The laws of physics do not merely permit consciousness, they require it, because without observers there is no measurement, and without measurement there is no reality. The cosmos exists through observation, and we exist because the cosmos observes. So perhaps we have never truly looked out at the universe. Perhaps everything we see, the stars, the galaxies, the faint echo of the cosmic background, is the interior of something, a reflection on the surface of space-time itself. The voids we call empty are full of meaning. The horizons we call boundaries are mirrors, and beyond every mirror there is only another reflection. Maybe that is the ultimate symmetry, not matter and antimatter, not energy and entropy, but perception and being. The universe looks back at itself through us, endlessly, across every scale. Each atom, each photon, each thought is part of that gaze. And as we stare deeper into the darkness, as we map the light that escapes from the farthest galaxies, we are not seeing something foreign. We are seeing the inside of the same infinite structure that gives rise to thought, to life, to wonder. Maybe we have never looked out at the universe at all. Maybe we have been looking from within. The stars, the galaxies, the horizon, each a reflection in the same cosmic cavity. We are not outside the whole. We are its heartbeat,